Of projects, one project that recently came up. I added a new project this morning, so it came up in the other class of mine, that is Calculus 1, and the discussion is the optimization, which is coincidentally what we do here. But the problem was, you may have seen elsewhere, and that is the problem of getting from point A to point B when there is a kind of a patch of rocket where they're laying a pipe, and there's a rocky terrain there, and then it is harder to go through that terrain than the rest of it. So you cannot go straight, okay? And so you have to optimize. Does it sound familiar? Right? And so then you gotta try to go like this, and this becomes x, and that is the optimization problem with one variable. Right, so that x, how far you go up. When it looks really bad, you want to cross straight through 90 degrees, but then it might not necessarily be the best choice. So then you pick x as this variable, and then your path becomes this. Okay, and then you optimize. You end up with a pretty cumbersome formula. And then what came up, it doesn't really have to be about pipes or anything else. Just it is moving through something that is impedes your speed of progress. Could be the terrain, or could be any kind of obstacles. So and then the problem seriously becomes way more difficult once you realize that it could be changing several times. So then you have something different in another patch, and once again it's more different, less different, and then there is a one variable to be also introduced as an extra parameter. Okay, and then imagine that these are changing continuously, such as for example you're climbing, and so if like this, so you from point A to point B, you're actually climbing, and then your speed of forward progress is might be proportional to the speed naturally. Okay, and then well, it could be different dependence. And then once again, how do you plot the project? Even though it appears to be entirely optimization problem based on Calculus 1, but really the number of parameters just explodes, and then so there are some sort of issues to worry about. Anyway, so that's it. Just adding an extra project statement to the list. In the meantime, we're doing optimization of problems of functions of two variables, and once again with the derivative. So let's the key to the method is on the picture on the right. So it is just like in Calculus 1, the means to an end, to that end, is to find where the derivative equal to 0. So this time it is not, if you want to, we have two derivatives. If we're talking about functions of two variables, then having two derivatives gives you two conditions on the increasing and decreasing behavior along one axis and the other axis. Say one along the x-axis, this, and along the y-axis, that. And as we realized yesterday, then both of these have to have a maximum point, and that is why you end up with these conditions, such as these. With respect to x, it has to have a zero derivative at that point, and with respect to y as well. Okay, so and then that works out the algebra very, very straightforward. Certainly, just twice as much work as in Calculus 1. Otherwise, it is very transparent. Notation, we have very nice abbreviated interpretation of those two. Both derivatives equal to 0 means that the gradient is equal to 0. Also, it means that the tangent plane is equal to 0, which is very clearly, you can clearly guess from this picture that it is the top of the hill. What is so special about the top of the hill? It doesn't matter in what direction you're going to go down. Okay, so means that the tangent plane has to be horizontal. If it has any kind of tilt in any direction, it means that you can go in the opposite direction, or in that direction, and you start climbing, and you're proving that it's not the maximum point. Only, of course, the caveat always the same: f is differentiable, because if it's not differentiable, then the two partial derivatives is not enough, because their diagonal direction might produce some unexpected change. There is no tangent plane to begin. So that logic falls apart. But other than that, this is the plan. But this is not entirely the full solution yet. So what needs to be spoken of a little bit of theory, and that is about, we don't really need, since we are looking for the, since we're looking for what, a short list of candidates. Then differentiability is not really a priority, because if you shorten the list, then it's okay. We're still looking for only the only necessary conditions. So then well, what is that? What do we need? We only need the differentiability, partial differentiability. So f is differentiable with respect to x at x equal a, x equal a, y equal b. Okay, and differentiable over y at that same point. Okay, so this is the point, this is a, this is b, this is z. Okay, and this is the point that we care about. We care about. We're trying to find it. Okay, and then secondly, we got to talk about derivatives. But really, before you talk about it, we have to use the same concept as in calculus 1, and that is local extreme points. And local extreme point, it means that there is an open disk around the point AB. So AB is a local max point of F if there is an open disk around AB such that for all points xy in the disk, we have that inequality. The same inequality, so f of AB is larger than or equal to f of xy. Okay, so in other words, you can have many ups and downs, but at the end of the day, you might have something like that. But you concentrate on one point, and what you do, you pretty much cut out a piece of the graph, but not like this. That picture suggests that I'm cutting off the top of the graph. The idea is actually elsewhere. We're cutting it vertically, not horizontally. So I go to the domain. Okay, and then I choose around the point, that point that we have interest in, AB. And I choose a disk around it, an open disk, so the boundary of the disk is not included. Okay, and then I build a cylinder on top of it, and with that cylinder I cut the piece of my surface like this. Okay, so it could look quite weird, like this. There is really no prediction of what it's going to look like. Okay, so and then this is my surface. That's what's left of my surface. The rest is ignored. Maybe there are elsewhere, there might be high point, lower point, doesn't matter, but the point is that in the vicinity of the point AB, this is that point is the highest. Okay? So the analogy is perfect with the dimension 1 when we had stuff like this, and then once again we had a point A, and then we limited our attention to an open interval. So this is an open interval around A. Okay, and once again, I'm limiting my attention to that open interval, but this time from below I cut a piece of my graph, which produces a curve. So a curve with the cut by two vertical lines produces a smaller curve. Okay, similar here, a surface cut with another surface appropriately located creates a smaller surface, and so the issue of the highest point remains, and then certainly we have the opposite inequality as a possibility, which it would be the mean. Okay, the same inequality. And then the Fermat's theorem comes into play, which we discussed yesterday. That in the former case, or rather the calculus 1 case, this is df dx is equal to of AB is equal to of A is equal to 0, and here the Fermat's theorem as a concept of application of Fermat theorem twice. Fermat theorem. Okay, so we have df dx. This is straight x of AB is equal to 0, and df dy AB is equal to 0. And once again, y we just talked about it. You are cutting that little surface now that we have found, and we cut it in two ways, along the x-axis and along the y-axis. So this is along the x-axis, say, and this is, say, along the x-axis. Okay, and both of these are kind of partial functions, if you like. So partial derivatives are derivatives of partial functions, so with respect to a particular one of the two variables, and then both of them are highest. Okay, and therefore the derivatives have to be equal to 0, or it's always a possibility it's undefined. The derivative might be undefined. That is, the undefined is the easy part to find out. The actual problematic part is that what you should remember from calculus 1. So once you found, so suppose we just did it yesterday, once all local extreme points are found, then what? What do we do then? There is an extra step of optimization.
You choose the maximum?
Right, yes, but there is what if we are talking about the oops. What if we're talking about optimization on an interval, such as like this? Okay, so suppose this is the interval and this is the function is not going to infinity either way, but it's defined on an interval. So remember the endpoints, right? So test the critical points, which is the ones that we found. These are critical points. And now we have the critical points for dimension 2 as well. Critical points, and number 1 and number 2, the endpoints. Well, now I don't want to say the endpoints because there are no ends anymore. Or there are ends, but we just call them differently. This is what we're talking about. So the interval has ends, right? So right here, one end, the other end. So just 2 endpoints to worry about. And now, so once again, endpoints plus endpoints to worry about. And now we are what are we? In what situation are we with dimension 2? So what are we looking at? Critical points where both derivatives are equal to 0. What else?
Places where it's not differentiable.
Well, this is not unfair to say. I would agree. In fact, it is actually a good way to put it. So, undefined derivative. But if the function looks, in this particular case, I tried to plot a smooth functions. Once I cut out that piece, where is the function is not differentiable? On the edge. Just like this function is not differential at the endpoints for a simple reason that for the function to be differentiable, it has to be defined at least in the vicinity of that point. Okay, so once again, y equal f of x is differentiable only if at a, only if it is it is defined on an open interval around a. Okay, so that's calc 1, and now we have z equal f of xy is differentiable at AB only if it is defined on an open disk around AB. The reason is they remember that the derivative ultimately is defined either partial derivatives or otherwise. No, the way we define the derivative, the gradient, is through a certain limit, and that certain limit was at AB. And remember how we define the limit. It is omnidirectional limit, which means from all directions you should be able to approach that point A. And the limit should exist. Before you ask does it exist or not, you should be able to approach that point from all directions. So if there is some of the directions are missing, then you cannot do that. Okay, so that is the assumption that is hidden inside of the differentiability condition, that the function is defined around it. In fact, you might remember that how you probably may have tried to get around this problem in calculus 1. You would define one-sided derivatives. One-sided derivatives at the endpoints when the function defined only one side of the function, you use the one-sided limit in order to define one-sided derivative. Okay, that it is not it's a useful concept, but not a lot of use for it in the context of optimization. Similarly, not similarly, the problem is that defining one-sided derivative or one-sided limit is difficult because there are so many sides, infinitely many sides. So I could approach a point if my point is not inside over here somewhere inside of my disk. So if it is unless I'm here, and then there's a smaller disk inside of which, and so everything is fine. But if I'm over here, on this over here, then no matter how small a disk I take around that point, it will hang out outside in part, and then it is simply not differentiable. Okay? So which means that the points on the boundary of our circle would have to be treated separately. And so we simply put them on the list. So what I put here undefined derivatives, but really, technically, critical points include undefined derivatives. That at least in calculus 1, and it's probably a fine idea just to take the points where derivative either 0 or undefined. And here I use probably better. Just to say that the boundary. So the boundary. Now so 2 points in the one-dimensional case. To add to the list, they may have 100 critical points, and then add 2. So like this. So in the beginning, say P and Q, and then a bunch of points inside, critical points, and so the list becomes only longer by 2. How many points for are there on the boundary?
Infinitely many.
Infinitely many. Every single point on the boundary is that. So in that infinity, in fact, they form a curve, and that is just the way we have to do it. And so let me carry out that plan once with a simple example. So f of xy is say x squared plus y squared. It is once again, let's pretend that we don't know what it is, and run through the plan. So d of dx is 2x. d of dy is 2y. Okay, set them equal to 0, solve, x equal to 0 and y equal to 0, so careful about that. Both of the conditions have to be satisfied, and that's how you create you produce a point. You have a condition on x and y, and then you may have end up with 1 point, no points, or many points, including infinitely many points. In fact, if you might remember a graph might look like this. Okay, so one of the derivatives will be definitely equal to 0 along one of the x's. And if you have something like this, so all of these are critical points. Okay, so like a cylinder on its side, every point at the top will have 0, both will be 0, this will be 0. Okay, so it is possible that you have infinitely many critical points. So okay, so the only critical points in this particular case is 0, 0. But okay, I didn't put it correctly. I meant what I meant is to maximize / minimize this function on a square. X between -1 and 1, and y between -1 and 1. Okay? So that makes a difference, that extra condition. So we're not maximizing, minimizing the whole thing, which happens to be this paraboloid of revolution. And so it's so easy to make to draw a picture of a paraboloid of revolution like this. It's a cup or something like that. But once I impose this restriction, you can try to think about what the graph looks like. So if I this is basically what is this curve over here. It is a level curve, and it is a circle because there's x and y symmetric. So it's a circle, and I'm cutting with horizontal lines. But as I said, we have to cut with vertical lines. So the origin, this is our origin of the domain of our function, and it happens to be a square, not a circle. So then we have to build a square on the xy plane and cut with. Okay, let me try it. So this is z, and my square is this. Okay, so my paraboloid looks like this. So hypothetically, it is if you cut vertically, it will be a circular top, but I have to cut with this. So can you try to imagine what it looks like? What's left of what part of the surface lies above this green square? What does it look like?
It's got 4 spikes.
It will have 4 spikes. In fact, we saw it once. I'll show in a second. But spikes will be at the corners. So roughly, maybe like this, spike, spike, and another spike over there, like this. Okay, so you can already see that what the result, our optimization problem will produce probably 4 maximum points. There was I could show you a better picture because we had it at some point. So surfaces. So there's a paraboloid here somewhere. Sphere sine tangent. No. Here it is. Okay, so that's a paraboloid. It's exactly that. If you look at the formula right here, it is x squared plus y squared. Okay, so and indeed it is automatically what that's exactly what Excel does. The domain is always a rectangle. Okay, so you actually have to try to figure out what the graph looks like if you want to cut it vertically, or if you try to change the domain from this rectangle to something else. Anyway, so that's the problem that we're facing now. What do we do to solve it? And we go on to, according to the plan, we have 1 critical point, and now we have to look on the xy plane. We have to look at the whole boundary of my domain. So the boundary of the domain, which is the whole thing. So in addition to the critical points that we have found, which is this one, okay, so all of these are also included, and we have to now take into account. It is funny because what has happened is that we have reduced our problem it is a reduction, but we are facing a problem pretty much, we are still facing an optimization problem with infinitely many possibilities, because we have a bunch of curves, right, you can see them over there, a bunch of curves to be maximized. So the 2-dimensional optimization problem the surface becomes a one-dimensional optimization problem with those curves. Okay, so specifically, this is what happens. I take the upper edge. Upper edge is, what is it? Y equal 1, x between negative 1 and 1. Okay, so that is pretty much what we have to do. We substitute this into my function. So I have f of xy is equal to, so x squared plus y squared, and I replace y with 1. In the meantime, x run between negative 1 and 1. So I have x squared plus 1. That is my function of one variable to be maximized. To maximize over x between negative 1 and 1. Okay, so that is literally an optimization for a problem of calculus 1. This is, right? This is calculus 1 optimization problem. And, well, fortunately, we can probably answer the question instantly. What's the answer? Function is x squared plus 1, maximize, minimize, over the integral x between negative 1 and 1. What's the answer? The maximum is?
At 1. Right.
At 1, and yeah, at 1 is 2 at x equal plus or minus 1, right? At plus or minus 1, this function of one variable reaches its maximum, okay? Similarly, we pick so this was the top, so that's the top, okay? The bottom is exactly the same, except, well, there's an absolute long difference, same. And once again, x run between negative 1 and 1, so in that answer still applicable. So the maximum is 2 at x equal plus or minus 1. Okay? Finally, we take left and right. And then once again, there will be, coincidentally, it will be the same. Here we say that x equal to 1 and y plus or minus 1. Plus or minus 1. And y is equal to, and y runs between negative 1 and 1. So then my function becomes 1 plus y squared, once again to maximize, over the integral y between negative 1 and 1. And so that's the same, pretty much the same problem. It has the same answer. Maximum, I forgot minimum. Okay, so maximum is 2 at x equal plus or minus 1. But minimally, we have to also take that into account. So what's the minimum? 1 plus y squared. What's the minimum value? What?
1.
1 at x equal, this is y, at y equal 0. Okay, same here. Minimum is 1 at y, at x equal 0. Okay, so these are the ones that are become, these are go to my list. These go to my list. In addition to this one at the top, I forgot to mention though that the function is at 0, 0 is equal to 0 as well. Okay, so these are the how many? It's actually, as you can see, these are these the same? The maximum points are the same, right? Maximum points are the same. These are y equal plus or minus 1, x equal plus or minus 1 is they're the same. It's the corners of my square. So what are they? Plus or minus 1, plus or minus 1. So f of plus or minus 1 plus or minus 1 is equal to 2. Okay, so they are all like within the rectangle, and the value is 2 to take into account, and it is actually larger than that critical points that showed me. Okay, so then we know that this is a maximum. Half of the job is done. So once again, critical points plus the infinitely many points on the edge of the square produce this conclusion. So at the corners of that square, the values are the highest, as we predicted, and they will all four equal to 2. Okay, the only thing that remains is minimum, and these are the minimum points. Both of them are equal to 1. Okay, so what's the conclusion? The minimum is equal to 1 at x equal 0 or y equals 0 on the edges. So in other words, we are here. So these points are already taken care of. These are max. These are max. Okay, those 4 points. What about these? They seem to be minimum points. They are not minimum points because
they're greater than the origin.
Because the origin is lower. The origin we have 0, and these are 1s. So these are 1. It is larger than 0, so no. This is yes, and it is the largest, and these are no. Okay, so the minimum is then f of 0, 0 is equal to 0 is the pretty much the answer. Okay, so that's how it works. So with the with optimization of functions of 2 variables. Now, 3 variables or higher, well, let's quickly think about it. Visualization becomes virtually impossible. So the domain, nothing really changes. So compute all partial derivatives, as many as you've got, set them equal to 0. If you have 10 variables, you have 10 partial derivatives. You'll have 10 equations with respect to 10 variables. Okay, so whether you want to solve it by hand or not is up to you. But then you still have to face the problem of degree 9, because your region, say maybe a rectangle, will have, well, it's not a rectangle really, but 10-dimensional box, it will have the boundary which is 9-dimensional. Okay, so and then you have to solve the 9-dimensional problem, optimization problem, before you can proceed, which is what we just did. It was easy because the functions were simple and familiar, and we have done calculus 1 was a while ago, so it certainly is easy. So as you climb dimensions, these are methods become harder and harder. So they become more theoretical than practical. Okay. So that's the optimization. Okay. So remember that the solution exists. The solution of optimization problem is always ensured when the domain is when the function is continuous and the domain is closed and bounded. So such as a rectangle is fine. If it becomes infinite, then there might be no maximum point or no minimum points, we don't know. Okay, so if it is not closed, if you can imagine if I excluded the edge of my even one point on the edge of my square, if I exclude it from the domain, then the function might not have a solution anymore, and it wouldn't have probably if I exclude all four endpoints. Then it will never reach the highest value. Okay, so partial derivatives, and which is something we didn't discuss a lot, but it deserves a quick discussion. It is a repeated differentiation. And so it was so easy in calculus 1. So you differentiate, and you have a derivative. And when you differentiate one more time, you have the second derivative. And on. It is pretty much a sequence of functions, which might converge to 0, not converge, but rather become 0. If it's a polynomial, it will become 0. If it's an exponential function, the sequence is constant, and if it is a trig function, sine function, will go in circles, and so on. Different kind of dynamics, but it's still a sequence of functions. Okay, and all of these, by the way, you might remember these are what the importance of these functions, and the sequence of functions is Taylor polynomials, because Taylor polynomials is actually puts in the sum what is f(n) derivative. Remember this one? You evaluated an n 1 away factorial. Okay, so n from 0 to infinity. So that's my Taylor polynomial. So all of the derivatives come into play. Now, what happens with a function of 2 variables? So 1 variable, 2 variables, 2 derivatives. So d dx d dy. Okay, so I have f sub x, f sub y. So this is the notation for the derivative. Sometimes especially when you do repeated differentiation, you just don't want to write primes anymore. So you limit it to the subscripts. So derivative of f with respect to y is simply subscript with respect to y. And then so you already have 2, and then if you differentiate one more time, you have 4. So this is f. Careful order of differentiation. So this is fxx. Okay, so x and then x. Here, however, you read it from right to left, so it will be yx. So this is ddx twice, and if you go straight, and then if you go up and then down, it will be ddy. And so reading from right to left, differentiation with respect to x first, then with respect to y. And this one will be fxy, because this is still ddx, and this is dy, gives me fyy. Okay, so there is a theorem that these two are equal. Sometimes. That certainly saves some. So the order of differentiation might not matter. We'll discuss that later. So that saves us some room, but otherwise the number of functions multiplies. It's like rabbits, frankly. So compared to one dimension, one derivative at a time, nothing is happening. And here you have more and more. If you continue differentiating and go to the third derivatives, you're going to have 8, and so on. You can imagine that Taylor series will have to be summed in this manner. All of these terms will have to be summed if you want to produce a Taylor series for a function of two variables. Okay? So that's certainly a problem. Anti-differentiation or integration, we are getting to that, but it's also a challenge also to be discussed, how to go backwards. Okay, so how to, this one was uncomplicated. That was the end of calculus 1 and the beginning of calculus 2. It's a technique that you develop, but otherwise it is straightforward. If you up to a constant, you can recover all the function from the derivative. Okay, so you know velocity, you know the location, you know acceleration, you can find the velocity. And here you have, it is also possible, but you need all the values. You need both derivatives naturally. You need both derivatives. From two derivatives, you should be able to recover both partial derivatives. You can recover the original function. Okay, and backwards you could start with second derivative, recover the third derivatives, and then the original one. So that part also works. So it's also still reversible, but you need all of this. That's why it makes kind of a sense to think. Well, that's why you do want to think about derivatives as one derivative made of the two partial derivatives. So that way things kind of look slightly better, only slightly better, because they have then you have one function, and then you produce a new function from it. And then you produce one more function from it. But you can see that even though it seems like a good plan, and it is, it's still the problem is that that's the main difference between this and calculus 1 is that the nature of the derivative, this derivative, which is say del f, okay, made of the two partial derivatives. The nature of that derivative is very different from the original function. It's just different in nature. It's not that it's maybe non-differential or something like that. The output is a vector. A function of two variables, it is a real value function. So the input is a vector, but output is a number. This new function is vector valued. A vector valued function, something that we haven't discussed yet, because this function has the input, the vector, and output is also a vector. Okay, so that's a vector field. That's why we can't really discuss the derivatives of functions several variables until we reach and discuss first vector fields at length. And then you can see the rest of the trouble. What if I take my vector field and differentiate it one more time? the nature of the function changes again, and we end up with something even more complicated. And then you can imagine that at every differentiation, the things will become more and more complex. Okay, so once again, we'll postpone that until slightly later, but there's one important topic before that we're going to discuss, and that's integration. And specifically, specific name for it is Riemann integration. So in other words, we're not going to talk about anti-differentiation until the time comes. So Riemann integration. So we'll have to very quickly review the Riemann integration of calculus 1. So function of one variable. Well, I'm not going to. Let's just give you the what comes at the end. The integral. So y equal f of x. The integral of fx dx from a to b is the area under the graph. Y equal f of x. Okay, now we are in a similar place, except now we don't have a plane anymore. We have a three-dimensional space, but the domain of the function might be once again analogous in the sense that if we started with a segment, now we have a rectangle, and it might be once again AB by CD as we just talked about. And then that is the domain, and above that domain lives our surface, the graph of the function of two variables, like this. So z equal f of x1. Okay, so and then you can guess what the integral. This one, the notation is tricky, so I'll just let me just use words for now. The integral of z equal f of xy over the rectangle R. So this is the rectangle. Well, you can guess what it is. So we have a curve and a segment, and the integral is the area under the graph. And now we have a surface. So what are we talking about? Under the graph. What is?
Volume.
It's the volume of the region under the graph. Volume. Okay, so quite naturally, you certainly have already seen some of it in calculus 2 when you computed, say, values of a specific, when the surfaces are specifically limited to what you can handle with a single integral, with this single integral, such as surface of revolution, for example. Okay, so you do some geometry, and then at the end of that, you still end up with single Riemann integral function of single variable. So now the difference is now the functions will be arbitrary as long as they well behaved, such as continuous functions will certainly be covered, and any shape of the region under the graph will be covered by this theorem. Okay. All right. So do something about the projects, please.